Um, when Andrews and Wendy invited me to... How are we doing? Yes, that's better. When Andrews and Wendy invited me to give this talk, I thought, well, I could talk more about stuff that I'm doing, or stuff about Haskell or GHC, but it'd be more fun, for me anyway, if I speak about something I know nothing about. So right up there, I committed to give this talk about the Lens library, which at that stage I knew nothing about except that everybody was talking about it. So I thought, if I commit to giving a talk about it, well then I'll have to learn about it, and I duly did. So in fact, I was at ICFP 2 weeks ago, so I had the good fortune to have Edward Kmet in person, who is a kind of force of nature, as any of you who've come across him will know. So I sort of had him pinned into a corner, so I had his undivided attention, which is a fairly dangerous state of affairs. But he does not get any of the blame for any of the misconceptions I tell you. I'm going to tell you my understanding, my sort of rational reconstruction of what the Lens library is about. I've only learnt about it in the last few weeks, so I don't expect that I know everything about it. So I'm very open to all of you both asking questions and making comments or observations as we go along. Let's do that. It's a small enough group. Let's be kind of interactive about it. That would be more fun for me. And also, I'm only going to tell you about a little piece of it, and it's vastly more general. But I'm going to tell you about a piece that at least I understand so far. Two other things to say. One is that I'm suffering from a sore throat, so I may be a little less frisky than I am sometimes, which may be a relief. The school that I'm the chair of governors of a school that my kids went to, and Ofsted are coming today. They phoned up yesterday. They give you 12 hours notice for the school. They are coming today, and they require the chair of governors to show up this afternoon. So I have to leave at lunchtime, which is really annoying because I was looking forward to the talks this afternoon. So if you want to talk to me, this morning is good. This afternoon will not be so good. Okay, lenses. Here we go. Here's the basic idea that I think probably most of you have probably already absorbed from the twittering about the Lens library. A lens is a kind of way... is a first-class value that gives you access into a data structure. So I'm drawing it here as a kind of the red line, that's the lens. And it's going to somehow give you access to a particular piece of a data structure. So the data structure, I'm always going to give it type S, and the focus of the lens, that is the piece of data it gives you access to, is going to be of type A. And a lens here is a first-class value that you can pass around, you can store it in a data structure, you can pass it as an argument, you can return it as a result. And it has a type, of course, lens SA. Well, it's lens prime SA for reasons that will become apparent later on in the talk. So, here's an example. If I've got a date-time structure, imagine this is a structure that includes dates and times. There's the month and the year and the hour and the minutes and the seconds. Then a lens that gets you from a date time to a minute. Here's the date-time structure, and here's the minutes inside it. Okay? So somehow it gives you access to that. Fair enough? And the big thing about lenses, of course, is you want to compose them. So if you've got a structure inside a structure, then you want to be able to stick these lenses together. So if the first lens takes you from S1 to S2, and the second lens takes you from S2 to some focus A, then you should be able to compose them to make a compound lens, which is a single composed value that gets from S1 all the way to A. So that's the result here. Okay? So this is one idea you must anchor in your minds. This is the whole thing we're trying to do, is to just build first-class values that gives you access into structures of some kind. Right. Okay. So, a concrete example. Well, first of all, you might think, so we can do this already in Haskell, can't we? And we can. So here is a sort of the standard example that everybody who talks about lenses has as their first example, nested records. We're going to have some others, but we're going to work with nested records for a bit. So here's a person record with an address field, and the address has a road, a city, and a postcode. All right? Now, if you want to change the name of a person, so you take a string, that's a new name, and a person, and want to deliver a new person. Then, so P is the person, N is the name. Then we use this record update syntax. You're familiar with this? You write P, that's the person value, open curly braces, and then field name equals value. So the field name equals, so that returns a new person with an updated name. Okay? If it becomes more awkward with a nested record, so here's how we update the postcode of a person. Well, there's the postcode. And here's the person. And what have we got to do? Well, we got to change the address field of the person. So it's going to P with the address field change. What's the new address field? Oh, darn, it's the address field of the old person, the address field of P. Oh, addr, remember, is just a selector function that takes a person to an address. So addr P is the address field of the original person, and then here's the update that updates the postcode. And this can get pretty tiresome if you're doing it many levels deep. You've probably all written code like this. I certainly have. It's clumsy. Okay? So far, so good? What we'd like to do with lenses is something like this. So I've used funny names here. So here's my person record again. I'd like to make a lens for each field that gives you access to the field. So lname, I'll call it for now, the lens for the name field, takes you from the person to the string. Laddr takes you from the person to the address, and so forth. And then I'm going to want functions that use a lens to do something to the record, and two ones that you come across immediately are view and set. Why I didn't call them get and set, I don't know, but I'm trying to use Edwards notation where possible. So view takes a lens from a structure S and a value A, and a structure S and gives you back the value. So that's like the record selector. And set takes a new value and takes an S to an S. But it's the same lens in both cases. So notice that the same lens lets you get or set. Right? It's the access field. If I had a compose lens, like, here's my compose L function, which I haven't told you about how to implement, but if I if I could compose them, now I can compose laddr with L postcode, that's laddr here, and the one that we get from postcode, and that makes a compose lens, which I could use for setting. So this is a more convenient way to set the postcode than the thing I had back here. Okay? More perspicuous, certainly, and easier to get right. Okay. So that's the setup. Are you with me so far? Please ask questions. But I'm going to show you a lot of code. And because we've got a lot of code and not very long, I'm going to go quickly, and that means I need you to tell me when I say something you don't understand, because I'd really like you to understand this code, because that's the fun bit. This is really a functional programming talk. All right, you're going to see lots of functional programs. Okay? Any questions so far? No. Okay. So what's this? Now, the obvious thing you might do, if you wanted to do this, would be to make a lens that had a getter and a setter. Right, so a lens is simply itself a record with a view field and a set field with suitable types. And now, of course, to view, to use, to write, to write view, you just select the view field out of the lens and apply it to the, and to do a set, you select the set field out. What could be easier, right? Just make a lens be a pair of functions that do the appropriate things. Yes? All right. So now we can compose lenses. We can write compose L, which has has this type here to compose the lenses together. And it's a little, you've got to think a little bit about exactly how you'd plumb these functions together. Here's the view. Here's the set. Oh, why have I called it U? I've called it U for update here. And to view, what have we got to do? We've got to, first of all, apply the first lens to S to get the subfield out, and then we apply the second lens for the result of that to get the subfield out of that. Okay, and update works similar. I think I've got this right. Okay, but it's kind of, it's a bit clumsy, and it's also a bit inefficient when you want to do things other than getting and setting. So modifying, here's modify, or what Edward calls over, which takes a lens and an A to A function, so it modifies the A field, right? Rather than retrieving it or setting it, it's going to have a function that applies to it, so it returns a new S, right, with a modified A field, like add 1 to it or make the address be in uppercase letters. So if we had this get and set thing, then in order to write over, we'd have to first of all get the field out, then apply F to it, and then set it. All right? So you can imagine that's maybe, I pattern match all my way down into this structure. Oh, I get the value out, I apply F to it, and then I pattern match my way into the structure again and rebuild it all the way up. Right? And if you wrote something like this by hand, you just pattern match your way down once, wouldn't you? Okay, so it's not kind of too cool. So what might you do? What might you do to fix this? The obvious thing to do is to add more fields to this record, right? Like this. Look, maybe we need, let's add modify to the lens data structure, right? So instead of just having set and view, it can have modify, which takes an A to A function and an S to S, right? But then you think, oh my, we might have other things we might want to do, like what happens if we want to have an A to maybe A function, so it can kind of fail, right? But then if it fails, I don't want to fill the field with a maybe value. I want to return a maybe of the whole record. Let's just pause on this. Are you okay with this function, modify maybe? It's a kind of conditional modification. You know, if the function returns nothing, then return nothing from the whole thing. Don't return me a record with a maybe field inside it. That wouldn't even be well typed. Wouldn't they so far? Or we might want to do I/O operations inside it. So here, I might want to have an A to, then I consult the phase of the moon and add that to the A value. And now, of course, I have to, the whole modification process is in the I/O monad. So you can see where this is going, right? This list is getting a bit longer. So things are not feeling good here. So far, so good? Oh, well, so now a Haskell program, as you look at this, and you think, these last two in particular, they kind of look similar, don't they? Maybe we can abstract over that guy. Maybe we can do this functor thing, right? Instead of A to maybe A and A to I/O, we can have an A to FA. And so there's a for all F here, right? It doesn't show up in the lens type. This is for every functor F. So now we're in better shape, right? So now, as it were, these two are just examples of, these two here are just examples of this one. So that seems more general. So that seems like a very nice idea, and that in fact turns out to be very much what Edward decided to do. So let me just remind you about functor. So for 90% of you, this is just revision, but let me just be sure that we're going to see a lot of functors. So I want to be sure about this. So functor is a class that has just one method, fmap, which takes an A to B function, and takes an FA to an FB. So examples are maybe, right? So this A here, oh darn, that should be functor F. I beg your pardon. So just read F where it says A. This F here has type star to star, has kind star to star. It's a type constructor, so we're abstracting over type constructors. And so maybe is a functor because if we fmap F over nothing, we get nothing. If we fmap F over just X, we get just of F of X. So there's a maybe of, yes, there's a maybe A in the result, okay? And the same for lists, except for lists, fmap is just the traditional map. It takes an A to B, and a list of A and returns a list of B, okay? So we're good with functors, and in fact, I/O is also a functor, so it'll work for that as well. Now you look at this, and what do you think? So this is the first time at which something amazing happens. Everything so far has been set up. Now you look at this, and if you're Edward, you think, maybe I could do these three using this guy. And that's the insight. So Edward's big insight was simply that you can have one function that rules them all, that does everything you want to do. So a lens is not a record of many functions like this, it's just one function. And that is the function. So I'm only showing you 2-parameter lenses at the moment. I'm not even going to get to the wonderful 4-parameter ones you probably know about. But when you look at this, you would never kind of dream this up out of whole cloth, right? When I first saw this type, I thought that's really weird. But now I thought about it like this, just generalizing away here. It makes perfect sense. But it kind of looks weird when you go back to view and set, because view and set don't look as if they have types anything like that, do they? Right? How can this one function do everything that we want for all these lenses? But in fact, it turns out that not only can it, but they're isomorphic. That is, if I take this definition of lens, which is just a type synonym, incidentally, so far, I'm going to get back to that at the end, it's just a type synonym, and I take this definition of lens R, I can convert lens R into a lens prime, and I can convert a lens prime into a lens R. And I'm going to show you how to do one direction and ask you to do the other one yourself. But I first thought it seemed really quite puzzling. It's a really nice little piece of functional programming, and it shows a very common idiom with which many of you will be familiar, but perhaps not all. And so I found it intriguing, so I'm going to just tell you about it. So we're going to go from, what are we going to go? From lens prime to lens R. That is this function actually expressive enough to do view and set? Okay? So a little pause. Are you okay with this for the moment? Nobody's asked any questions or made any observations, which is slightly ominous. Yes, Tom. Tom. Oh dear. So, all right. So, Tuan, right. Thank you. for the benefit of people watching this video, they've been pointing out that Twan probably invented this. So I'm looking at it through a lens, right, at which Twan and Edward are sort of are lined up. And Edward is larger and more recent, so he obscures all that lies behind. Sorry, Twan. Thank you. All right. So, how are we going to do the set thing? What I want to do is I want to build a set function out of this lens function. How am I to do that? At first it looks a bit weird because what we got, this ln guy, he's the lens, and he has this strange functory type. And what we want is a function, so we want thing that goes, so I'm just going to do the set part of this, right? So I'm taking a subproblem. Take a lens to an A to S thing. Right? How am I to do that? Well, what this guy ln does is he returns a value. That's all I can do to the A value, right? So he returns a value here that is an fs. But what I want is an s. So I somehow got to get from an fs to an s. So if I choose a suitable f, that could be quite easy. So it's just the identity functor. So here's identity. New type identity equals identity of A. So as usual in Haskell, we're punning the name of the type with the name of its data constructor. Run identity is just comes in the library. This is all, weirdly, this is in data.traversable or something, but it may move. It seems a very weird place for it to be. Identity, that should say identity. The data constructor takes an A to an identity A, and run identity does the reverse. It takes an identity S to an S for some reason. I changed the name of the type variable. And identity is a functor, right? So in the obvious way. So I can F map over it. Okay? So now, so what you can see is I said here that we had an FS coming back from the lens, but we wanted an S. So identity is what we want because an identity int simply has a payload of an int, or an identity of S has a payload of an S. So that's what I want. So here is, in fact, the code that does the job. What happens here? I'm going to let's see. Let's pause for a moment to look at this code. Here's the type. Here's the thing that I'm writing. Set has type, takes a lens and returns an A to S function. So this ln thing is the lens, and it is a function of this type up here. So I'm going to need to apply it to a function which is going to operate on the field. That's why I call it set field. So it's an A to FA, or it's a field function somehow. It's an A to FA function. And I'm going to apply it to S, which is the record itself. So the lens applied to S, I'm going to apply it to the function and the S. So what is this set field thing going to do? Well, it's applied to this argument here is the old value of the current value of the focus. And we're not interested in that because we're trying to set it, we're trying to overwrite it. So we can throw that away here, and then we're just going to return identity of the new value, right? So, so this new value, x, is of type A, right? So that x is of type A. So this function set field does indeed have type A to identity of A. It throws away the old value and just returns identity of the new value, all right? And now what? Well, now ln takes that A to FA function, A to identity A function, and lifts it to an S to identity S function. By the magic of, we haven't seen the implementation of ln yet, but this is its type. Okay? So now all set has to do is to remove the identity constructor, which is now wrapping the record. Okay? So it's very, very simple in a way. So it's kind of, it's almost embarrassingly simple. You look at it and you think, how on earth does that work? But it does, and all we're doing is we're using the new type to just dress up the type class mechanism so that Haskell knows, or GHC knows, which dictionary to use. So when we do the fmap stuff, we know to use the instance for identity. So now Edward would write this in point-free style, right? He would write it like this. So S here is the last argument, right? So this is run identity dot ln of set field, right? So run identity dot, I've removed the S parameter here, and then I've recast set field as identity composed with const x, const being the function that throws away its argument. So when you read Edward or Twan, or indeed lens aficionados programs, they often write them in this point-free style that looks like line noise until you get used to it. But it's kind of compact, and once you get used to it, it has a certain eccentric charm all of its own. So I'll show you some examples, but I tend to write in point-full style myself. I find it easy to understand. Okay, so this is the point. Does this code make sense to you? Please say if it doesn't, because we're going to see a lot more code like this. All right. You're being very, yes, yes, yes. Why I've gone to length to protect them from what? So can I rephrase your question? Are you saying that in this use of set, I'm picking the functor, namely identity, and so the client, the person using this lens, doesn't need to know that there's a functor blah wrapped up inside there? Is that what you mean? That's true, but it is very convenient just to be able to call set. Right? That's not the only thing we're going to be able to do, and indeed, there's nothing to stop users of lenses using them in all sorts of other ways too. But this particular function needs to use it at this particular type. You see what I mean? So for other functions, they'll use it with other functors. And you can write ones of your own. So we're not protecting the user from it. It's more like we're saying, if what you want to do is set, this is the functor you want to use. And personally, I would rather write set blah blah than I would write run identity.ln of identity.const, personally. But maybe you're built differently. Okay. Let's see. Oh, but we can immediately do over. Do you remember that over that was rather inefficient because we had to do a get and then a set? Well, that comes out very conveniently now because instead of this const, do you remember I said this guy throws away the old value, returning the new value? If instead of throwing it away, we apply f to it, then we get over. All right? So all we just do is, remember, here we got const x, and we got an a, and here we got f instead of that, and an a to a function. It's very simple. So now, as it turns out, by the time we work this out, and I'll show you an example in a second, we don't pattern match our way down the structure twice. It all happens nice and efficiently. So that's kind of convenient. Okay. Now, so let's just do the same again then with viewing. We're going to do, we've done set, let's do view. So this seems a bit more puzzling. Well, it did to me at first. Look, we've got a lens. What is view? It takes an S to A. So we need something that takes a lens to an S to A function. So now, what the lens returns is an FS. But what we want is a value of some completely different type, A. So how on earth are we going to get from an FS to an A? That seems weird, doesn't it? Well, it seemed weird to me. But of course, the trick is you pack the A inside the F using the constant functor. Let's see. So new type is takes two type parameters. Sorry, this const is a new type which takes two type parameters. V for the payload, and A is a kind of phantom parameter that isn't used on the right-hand side at all. So it's a bit like that const function, right, that we had over here, that had a payload that it kept and a second argument that it threw away. This const guy is the same thing at the level of types. He throws away his second argument, but his first argument is actually inside the value. A const value carries a value of type V, but the A argument, the second argument, is phantom. Right? There's no value level reflection of it. So getConst takes a const VA and gives you a V, so it just unwraps one of these const things to give you the payload. Now then, const is a functor, but it's a functor in a slightly weird way. What's surprising about this code? Not to you, of course, but to a more early Haskell programmer, what would be surprising? Somebody other than Duncan. Yes? Yeah, it never uses f, right? That seems kind of weird. If there's this a to b function, and we start with a const, we come up with a const va, and we're going to get a const vb, but we don't use f. But of course we don't use f, because const here, you know, the second argument of the const, which is the bit the a or b stuff is happening to, doesn't show up at the value level at all. All right? So it's you write this down and type checks, and it all look. There's something very strange going on here. But it turns out to be exactly what we need for our application. So here's const again. Now, what are we going to do view? Well, we're going to apply our lens, ln, right? Here's its type again. You're going to get terribly used to this stuff at the top. And we're going to apply it to const. So what type does const have? Well, const here has type v to, what does it have? It's type v to const va, right? But here I'm going to use it at type a to const aa. Right? I'm going to instantiate const. I don't have to do that explicitly. Type inference will do that for me. But this particular occurrence of const, think of it as having type a to const aa. Does that fit the lens's argument function type? Well, yes. With f equal to const a. Good. Okay. So it fits this type with f equal to const a. So then if I apply that to an s, what do I get back? I get f, remember, is const a, so I get back a const a s. Hallelujah, brothers and sisters. We can then say get const to, where's get const? Here, to pick out the payload, which is the first argument, which is an a thing, right? Which is just what we wanted, because view was meant to get the a thing out, not giving me the record back, but giving me the focus back. Isn't that kind of weird? Well, I thought it was kind of weird. But it's rather lovely as well. So these two very sort of, almost vacuous-looking new types, identity and constant, that use this function to do both, the same function to do both views and setting. So now I can do the whole thing. Lens to lensr is just let me use these two functions and make them the two things at the record. So there's the isomorphism in one direction, okay? And you can write that isomorphism in the other direction. So if you get a little bored, just get a little sheet of paper and try it. There aren't many ways to do it. The types practically tell you what to do. But I've got other things I want to tell you about. So now we've got sort of got some idea of where that type came from. Let's see how we can use it. So far, I've told you how you can use a lens, but I haven't told you how you can make a lens. Well, here's how you can make a lens. So take our favorite record. This time I'm going to give them underscores here for reasons that will become apparent, because I really want to use the name as the name of the lens rather than as the name of the record field. So there it is, person with two fields. It's a smaller person, just a name and a salary. And what's I want a lens between person and string. The string is going to be the person's name. So what am I going to do? Well, what is a lens? It takes a function, that's this element function of type a to fa, and a person, a pns, just two fields, name and salary. And then what has it got to do? Well, it's got to return a function from s to fs. But what it's given is, this element function, is a type from, in this case, string to f of string. And this has to work for any functor f. So elt fun of n, what type's that? That's going to be f of string. But what I don't want an f of string, I want an f of person. How do I get from an f of string to an f of person? Answer by f mapping, of course, because fmap has type a to b to fa to fb, and in this case, the fa is going to be the f string, and the fb is going to be the f person. And what is my string to person function? Well, of course, it's just the function that replaces the name field. Right, so here it is, lambda n prime, that's the new name, p of n prime and s, the very same salary, right? So that's always good. So I think of this as being like this function is like a data structure with a hole in it, right? It's the person data structure. It's this data structure with one of the fields abstracted out, that's the n field, and made into a function argument, okay? That's all. So now I've made a lens for the name field. I can do a similar one for the address field, right? And in fact, you'll see a lot of stuff. The fmap, writing this fmap at the front is sometimes a little bit tiresome syntactically. So dollar, this angle brackets, dollar angle brackets, is just a synonym for fmap. It's defined in the functor library as well. So you can write fmap infix. So you'll see lots of code like this. The wrapping function applied to the element function itself applied to the actual focus. Okay? Good? All right, now, what can we do? Well, we can use this lens. So if we got, and you can actually, I'm not going to do this live, but if you got, here's the function I just wrote. And if you define a record Fred here, and then say view name Fred, I get his name back. And if I set name to be Bill of Fred, I get the record with an updated name field. Right? So it's the very same lens in both cases. That's the only point I want to keep making, is that there's one lens value which I just use in various ways to get access to the field in various ways. And I could do over as well for this and other things too. Okay? All right. So, to me, though, when I first started doing this, I thought, there's still some kind of magic here. It's as if I know how GHC works because I wrote it, and I've seen all the code, right? So I ought to know how everything works. And yet, when I type view name Fred, I can't figure out what's going on. So here is how it works. Look, view name Fred. Here is Fred, right? How does that name get popped out of this function? Well, if you just inline view, remember what was view? Get const of lun const, the lens applied to const. So get const of the lens name applied to const and the record. It's the very same record. So I've just inlined view at this point. Now what happens? Let me inline name. What's name? That's the lens. Here's the lens. So it's get const of, now there's an fmap from the lens here, and there's the wrapping function. That's the data structure with the hole in it, applied to const applied to Fred. Const, that's the function here, and it's applied to Fred, in this case, the field. All right? Now, what am I going to do? I'm just going to see what fmap does. Fmap, remember the fmap instance for const. Remember, I drew attention to this. It didn't apply f, it just returned const of the very same value. So this fmap of f here over this const, it ignores this function and just returns you const Fred, and then get const unwraps it, and there you are, as if by magic. So the place where the fmap threw away the function was precisely the place where the wrapper, that is the reconstruction function, got discarded, leaving only the value to return. That's all. So it's kind of, it's just lambda calculus. All right? All right. Now, so what have we seen? We've seen how this one function can do sets and gets. We've seen how to build lenses, and we're going to see how to compose them. Yes? Oh, yes. Yes, the bit about new type not having a runtime cost. So I've used several new types here, right, in some of these functions, like these ones, right, new type constant. You might worry, does this involve actual construction and deconstruction at runtime? So no, it doesn't. So new types are guaranteed free. Using a new type, so if you say const of x, or if you do this pattern matching thing, this operationally is an identity function, right? It doesn't actually evaluate something, pattern match on it, fetch something out of the heap and return it. It just returns its argument, operationally. It changes its type, of course, from const v a to v. So new types are free in that sense. Oh, wait. So I'm not saying, when I say new type has no runtime cost, I'm not saying that all this will necessarily happen statically. Actually, quite a lot of it will, because I think view is sufficiently small that it will get inlined automatically, and I think even Edward in his library puts an inline pragma on it, so it will. And so once the things get inlined enough, all of this will happen at compile time, or quite a lot of it will happen at compile time. But the point I was really making here is that there's no construction and deconstruction for these view and const things. That the new type idiom is really just a way of saying, which particular fmap did you mean? And it's a funny Haskell-ish way of saying in the terms what you'd really like to, the type at which you would like to call this function. But That was one of the more, I don't think we really expected new types to be quite so ubiquitous in this kind of way. The interaction of new types and type classes was much more fruitful than I at all expected when we designed the language. Yeah, anybody else? Okay, let's just compose lenses. So this is the same picture as I had before. I want to compose, how am I going to write composel? So this was another little surprise to me. So I want a function which takes a lens of an S1, S2, and lens of S2 of A to a lens of S1 and A. So let's write out the type of lens. Remember, here it is, right? It's going to be at the top of every slide, just to remind you. You'll be seeing this in your sleep. You'll have strange dreams about func to F, double arrow, A to FA, to S to FS. But they'll be good dreams, right? They'll, you know, lovely things will happen to you. So now here's the first lens, then, this guy, has type, look at it, it has type S2 to FS2, because A is S2 here, to S1 to FS1, look, right? And this guy has type, well, it's an S1 to A, so it has an A to FA to, did I get this wrong? Darn. No, it's this one, isn't it? To an S2 to FS2. I didn't get it wrong. So now, how can we compose these together? Well, they're just functions, right? And in fact, the result of this function is the right shape to be the argument of that function. So in fact, I can compose lenses by just composing the functions with function composition dot. This isn't a sort of weird kind of some other dot. This is ordinary function composition. It's kind of cute. I don't think it's in a way that important, but it's certainly very notationally convenient that lens composition is function composition. Because lenses, as we'll come back to afterwards, are simply a type synonym. They're not wrapped up in some new type or some data type to conceal them. They're rather transparent, right, for reasons we'll see. But one of the reasons that we'll see is that then we can use ordinary function composition dot to compose them. Okay, so that's a little kind of, it's a neat trick. I don't think this is sort of deep or fundamental, but it's a very nice trick that you can use ordinary function composition to compose lenses. Okay? Right, so now, oh, and the last thing is then to build these lenses, let's see, we've got records, and all this code here that I wrote for you, that's boilerplate, right? I could crank it out every time, but Edward has kindly automated the process for us by, you write this data type declaration, you import the right bit of the lens library, and say make lenses, and it sort of spits out this code, one definition for each field. And there's various variants of this that let you control the names of the lenses and so forth. But by default, it'll sort of strip the leading underscores. Okay, so it's just a convenient boilerplate generator. All right? So, let's see. That's, now, having done that, we've got person and address. We make lenses for both of them. And now we can do our set postcode thing again. We're back to the beginning of the talk, just by composing two of these lenses together with ordinary function composition. And so now it begins to look like a path into a data structure. That's quite nice. Okay? All right, yeah. Yeah, so I think you're kind of asking for a library which is exposing an abstraction. If you expose the representation of the abstraction, you're sort of laying yourself open to all sorts of kind of jiggery-pokery. And you are. But there are advantages to it too, which I'll show you. And I think this is something one might question about the lens library, if you like. So it's the first abstraction that is kind of transparent but has a reason for being so that I've seen. Mostly, I like abstractions to be completely opaque. But there do seem to be quite good reasons here. We'll see more of them as the talk goes on. But it is a synonym and not a new type. Right? And so, yeah. All right. Now, more line noise. And I'm not going to go through very many of these functions. The lens library is very large, but it has a whole bunch of little infix operators which do some of these things. I think I've got this right, that dot twiddle is set. So instead of set address.postcode, I think, you can say address.postcode.twiddle of PC, and then $ is our usual infix application. So you can write things that look like this with no parentheses, and I think the precedence is such that it all works out. But you need to sort of get used to reading this stuff before it makes any kind of sense at all. We can write obscure Haskell programs very easily. And I think that's true of any library, right? The library is effectively exposed domain-specific languages to write your programs in, and if you don't understand the abstractions, then you're not going to understand the code. But the API of Lens is particularly large. I've been using rgrep a lot to search through the library for where is, dot up arrow, dot defined. I don't know. All right. Now, let's see. We earlier talked about some of these things, right? A to maybe A to, right? Remember I said it would be nice to be able to do those? Well, of course, those are particularly easy because they had exactly the shape that I wanted for the lens. So in a way, this is a partial answer to your question earlier, right, which is that here I want to instantiate f with maybe and here with IO, but lens already is such a thing, so I don't need to do anything to it to make it have these types. It's kind of modify m is really the identity function, and modify IO is the identity function. You could really write these type signatures and then write underneath modify m equals ID, and they would all type check. It's rather cool. Okay, so the other point, the point there is then that lenses give you this sort of generality that says, well, look, I can make this work for any functor f. Const is useful, ID is useful, but all other functors are also useful. So that's one, as it were, dimension of generality that lenses give you. What came as a completely surprise to me is that there are completely other dimensions of generality, which I will get to very, very shortly. Damn, we're running out of time. Okay, so let me tell you quickly about some applications. So now we've got all the pieces. I wanted to look for applications that didn't involve just nested records. Right, so I asked on the mailing list, some of you will have seen my messages about this, and I've collected just 3 or 4 examples to show you very quickly. So here's virtual fields as an idea that says you might have a data structure that contains things that feel like fields, that is, I've got a lens for them, but there isn't really a field there at all. So here's a temperature containing a Fahrenheit, its representation is the temperature in Fahrenheit, but I have a lens, centigrade, which gives me a way to get from the temperature to the centigrade temperature, right, as a floating point number. Of course, I'm not storing the centigrade temperature inside here at all, so I'm not really accessing a field of the data structure. And what do? Well, I have to build a lens. And what is a lens? Darn, I didn't put the type. Remember, it's this guy. So I must take an element function. That's the function that's going to apply to centigrade values, right? So, but what I've got is a Fahrenheit value. So what I've got to do is I've got to take the Fahrenheit value, apply, some Fahrenheit to centigrade function to convert to centigrade, then apply my centifun to it, and then I've got to fmap, as before, something to put the thing back together. This is the wrapping up business. But before I wrap it up, I've got to convert it back to Fahrenheit. Easy, right? So that's quite nice. I've got a way of reaching into a data structure to find a field that isn't really there at all. Kind of good. Invariance, here's another one. So this is several people suggested this one to me. There's a couple of packages out there that do dates and times. There's a couple of them. And so they have, I'm just going to stick to times here, hours and minutes. Now, supposing I have, hours is 3 and minutes is 58, and I want to add 4 to the minutes field. Do I want to get minutes equals 62? No. I want to get hours is 4, minutes is 2. Is it easy? It's easy. What have I got to do when I build my lens? It's all in the lens for minutes. This is not automatically generated, of course. You really have to write this. So this is the function that works on minutes. Remember, it's going to take a minutes to an f minutes. So, well, let's see. And then I've got to do this wrap business. So, did I get this right at all? No, I didn't. I should really say mod. Hang on. Oh, yes, I did. Right. So minutes functions is just going to say add 4. So I might get 62. But in the wrapping function that takes the minutes field and wraps it up into a time field, the wrap function here is going to say, well, if the minutes is bigger than 60, I should subtract 60 and add 1 to the hours. If it's smaller than 60, smaller than 0, I should add 60. And really, you should do a mod thing here. But I left the code simple. If you added 150, this wouldn't work. But I'm doing a simple version for here. Does that make sense? So I just want to get the idea that I think it's really nice that, and then what you get is a lens, right? You can think of it thereafter as a record field, right? It has all the properties of lenses. So another example, non-record data structure. So here's finite maps. So here I want a way into a finite map. So map kv, this is from data.map, is a mapping from keys of type k to values of type v. And you can do lookups and inserts and deletes and unions on these finite maps. It's a very well-established library. So existing library, but I want a lens that will, it's a parameterized lens now. Look, this lens at takes a key value and gives me a lens whose focus is the value that's bound to that key, if there is one, right? So, but since there may not be one, it had better not be a lens from map kv to v, it had better be a lens from map kv to maybe v, in case the thing isn't there, all right? And it's quite easy to write such a lens. Oh, once I've got this lens, right, so at 3 would be the lens that says the value in the map for 3, then I can get it and set it and view it and modify it and so forth, you know, and compose it with other lenses. And what have I got to do? Well, you know, so here's the key value, and there's the function that works on the element, right? That's the function that's going to work on the individual element. So what type is it? What type is mubfun? It's actually maybe V. I should have, so it's an A to FA, right? But the A here is the element type of the lens. So it's actually going to be, mubfun has to be maybe V to maybe V, right? Because in this case, that's what I've instantiated the A bit of this particular lens, right? Did I get this right? I hope I did. Where's mubfun? Did I do the right thing? What? Mubfun of MV? Yes, that's right. So lookup, the lookup from the map library returns a maybe. So mubfun applied to this maybe gives me back a maybe. So this, the argument that wrap is applied to is itself going to be a maybe v, right? And what does it do? Well, if it was gives me a new value, just v prime, then I better insert that into the map, thereby overwriting what was there before. And if it's nothing, then I must delete it from the map. Easy. Unless it wasn't there already. I think, does delete complain if it's not there already? Yeah. Where? Oh, mubfun. Yes, yes, absolutely. Yeah, yes, yeah, sorry, quite right. It should be, it's maybe v to f of maybe v. Absolutely right, thank you. And that's why I need to f map this. Beg your pardon? Oh, in this case, the f is a maybe as well. No. No, in this case, the f is not a maybe as well. The f is this f, right? We're building a lens, right? So since we're making a lens, this at is meant to be a lens. So there's really a for all f involved here. So it really is a maybe v to f of maybe v. Yeah. And maybe I left a few type signatures and code out of here, but I thought you were getting better at this. But it does make your head spin a bit. And then you write the code and it all works. You think, oh, this is cool. So I thought that was kind of nice, a way into a data structure. Here's another example of a way into a parameterized lens into a data structure, and that's bit fields, right? So if I want a lens that lets me take an int and give that access to a particular bit in that int. This is not a record field, this is a bit field. That's fine. It's parameterized by which bit number I want. So if I say view 3 with bit at 1, I get true because it returns a bool, well, you know, true and false for the bit being true and false. And in fact, in the actual library, this is supplied as part of Lens. It's, of course, generalized not only for int, but for any thing that has bits. Haskell already has, the libraries already have a type class for bits. So I think, so these are just the examples that the simplest examples that I came across that I thought were easily comprehensible. Then somebody sent me this example, which is a web scraper, apparently, right? And it's from a hexpat lens. And look at this. So somehow you can see some weird stuff is going on. He's going into all the nodes, and he's doing all the ones that are named A, and then all the ones that have something to do with hrefs, and then he's filtering out all the ones that are local. You can see that there's quite a lot of stuff going on, and all these dots are lens compositions. So I don't even understand this, but I don't propose to try to explain it to you. I just want you to give you the sense that the bits that we've seen here are just the start, that people go very, very far with this. All right. Now, 9 minutes. I want to show you the second amazing insight. Any questions at this pause point? Yeah. Yes, it does. Yes. Yes, yes. So the things like this, yes, that will not be generated by template Haskell. So the question is, would there be an easier way of writing functions like this? Could we, after we've written a dozen such lenses for different kinds of data structures, could we spot a common pattern and automate that a bit? Maybe. Maybe. Go for it. I don't think that's been done. Does anybody know of any? Yes? Oh. Right, right, yes. Did I mention that the lens library defines 94 type classes? So, as I'm going to tell you at the end, I've been lying everywhere, right, by dramatically oversimplifying everything. So, I can't confidently say that it hasn't been done, but I think, so there's some generalization of this, but I don't think there's generalization in the sense that you make. So, take random data structure and sort of somehow make it easier or more automated to build the particular lens I want. But maybe there is. Right, right. One thing I don't like about this is I think this lens ought to be built into data.map, right? Because I don't like the idea here that I'm looking up and then either inserting or deleting, because that means I'm doing two traversals over the map to do this one thing, right? And that was what I said lenses were more efficient. So in the end, I bet this lens ends up in map. Because it can walk over its very clever data structure, balance trees or whatever it is, and do the right thing in a lensy kind of way. So I think slowly lenses are going to percolate more deeply into our libraries. Yes, it has, but I don't think modifies has a type that's as general as this. And if it's not as general as this, it can't be a lens. So it's stuffed. So I think it'll end up. Yes. Does a lens library? Actually, that's a good question. The lens library does depend on a couple of dozen other Edward Comet libraries. So it's a I believe, yes. You say Cabal install lens, and the internet goes dark for a few minutes while your computer gets very hot, and GHC has a panic. All right, I've got only 5 minutes to tell you about a glorious thing, which I can't not tell you about, which is and this was a total surprise to me. We've talked about the generalization of lenses by instantiating F, but what's more amazing to me is that by changing the type class here, you get a whole new kind of thing, not a lens at all, from functor to applicative. In fact, what you get is a multi-focus lens. Right, so instead of pointing to one focus, it points to multiple foci, right, all of the same type A. So it's called a traversal, right, still a container of S, and multiple foci of type A. So I've got to tell you, remind you very quickly about applicative. It's a type class like this. It's like a weak kind of monad. Look at its types. Pure is like return, and this angle bracket star is a bit like bind, but a bit less general. It's a bit weaker than monad. It's an F of A arrow B and an F of A, and it applies the function part to it applies this function to this value to get a B and gives you an FB. Okay? Now, let's just see how you can, why would applicative support multi-focus lenses? What does that mean? So here's the way I've been thinking about it. The bit I've shown you already is that an ordinary lens takes a data structure and splits it into the element, in this case the road of the address, and everything except the road, the wrapper. So here's the wrapper piece that is, lambda r prime a r prime cp. So that's the brown circle, right? And here's the element function applied to the road. That's the blue piece in the middle. But if what we want to do is to have two foci, so instead of focusing just on the road, we want to focus on the road and the city, but not the postcode. Right, there's 3 strings here, but I want to focus on the first 2, because I maybe want to make them go lowercase, but I don't want to do that to the postcode, right? So I want a lens that points to road and city. How would I do that? So I'll call it address-stras, so it's a traversal from address to string, right? So it focuses on the road and the city. So it's going to take and somehow it's going to do the same as lens. It's going to apply this element function to the road and to the city, right? But not to the postcode. And then here's the wrapper piece, something with 2 holes in it, lambda r prime and c prime, and then I form the address with the new road and city, but the old postcode, okay? So those are the pieces. How can I fit these pieces together? Well, because here I fitted the pieces together with fmap. But fmap isn't powerful enough to fit these 3 pieces together. Whereas look, I've got a string to address, and I've got an F string and an F string, and I've got to glue them together somehow. Well, those of you familiar with applicative will know exactly how to do it, and you're going to need to use this guy. Because if we say pure of this wrapper, then I get an F of string to address. And if I have an F of string to address and an F of string, I can get a F of string to address, and then I can apply that to this guy. So here's the code. So I say pure of the wrapper, and then I use the angle brackets apply to these things, and that's all there is to it. Right? So do you see, what I want you to get a sort of gut feel about is the way that by using applicative, which is a bit more powerful than functor, but not as hairy as monad, right? That applicative gives you the opportunity to combine multiple things, and that's what gives us the multiple foci of our lens. Okay? Now you will see things that don't look quite like this. You'll see them looking like this. Because in fact, pure of something, angle bracket something else, is, if you work out the types, it's the same as fmap. So there's fmap again, and we're using a sort of functor map here, and then we need the applicative thing for the next thing. So I'll leave that on the slide for you to look at later. Now, what can we do with these traversals? Well, traversals are amazing. Look at this. We can, supposing we simply did something very rather dumb and said, supposing we just took over, this very same over, here's the over that we wrote before, and here it takes, so it takes a lens and an A to A function and gives you an S to S function. All right? Now, supposing we simply crossed out the type signature, or rather, supposing we gave it a traversal, let's say. Could we give it a traversal and take an A to A function, give an S to S function? If we could, what would it do? Well, presumably, I'd be applying this A to A function on all of the strings that were the focuses, the foci, right? So if I said over of, lowercase or two lower over some address, I'd make the road lowercase, I'd make the city lowercase, and I would not be touching the postcode. But can this possibly work? Well, actually, if you simply write this code, right, with this being a traversal, it does. And why does it work? Well, because all we need is for identity to be an instance of applicative, which it is. So as if by magic, you kind of get this to work out. And in fact, here it is, over of adjusters of, and then two lower, that's the function, right? So here's the lens, the function, and the record, the lens, the function, and the record. And we'll just make the address and the thing lowercase, but not the postcode. I think that's very cool. So lenses with multiple foci. Just going from functor to applicative gives you lenses with multiple foci. And it turns out then that you can do the very similar thing with view. At first, it seems impossible. After all, look, if I've got view, if I take a lens that focuses on multiple things of type A, how can I possibly get back one thing of type A? Because there's multiple of them, right? So if you type this in, it won't work. But, and then you think, what's going wrong? Well, what's going wrong is that we need const to be an instance of applicative. How can const be an instance of applicative? At this stage, I'm out of time, so I'm just going to tell you that the applicative instance of const requires the element values to be a monoid, so that I can combine them, right? So they precisely gives you, monoid here, precisely gives you the ability to take two A values and smash them into one. And so now viewing, right, with on lists, the monoid for lists is just list append. We'll just concatenate all the addresses. So it gives you a kind of fold. Okay, so I'm going to wrap now because I'm out of time. But last thing I want to tell you about traversals is we're so used to thinking of kind of lists of elements, and we map over a list of all the elements. We're not used to thinking of non-uniform foci. I'm stopping. So you could have a traversal which focuses on every alternate element of a list, or the even elements of a tree, or the people in a table whose addresses are within 50 miles of a particular place. You see what I mean? Very non-uniform foci. I really like that. It took me a while to get a hold of it. Right, so I want to tell you, stand back a bit before that. We've already discussed that lenses are not abstract, and I think the reason that they come out as non-abstract is because that leaves open this extra wiggle room for adding applicatives and other things. I think that's the main reason. Otherwise, I think the jury's out about whether this is a good thing or not. Yeah. Oh, that's right. There's a sort of that's a tiresome engineering thing that you can make a lens without depending on the lens library. Yes. Yes. In practice, that's quite useful, but it kind of oughtn't to be. I regard that as something of a language flaw in a way. Everything I've told you is a lie, right? Here is the real type of lens. A lens has 4 type parameters, and lens prime is sort of specialized, so these are type-changing lenses. And over, I gave you this type. Here is the real type of over. I have no clue what a profunctor is or what setting is. So, I mean, Edward needs help here. He has sort of, in fact, the lens library I counted 94 modules, 69 classes, 39 new types, 34 data types, and 194 type synonyms. And these type synonyms are not simple, right? They are these kind of scary lens type synonyms like this one. So there's a lot of detail here. This stuff goes very far. But at least he writes, in comments, and in the Haddock comments, you'll see he writes lots of more specific. So if traverse of has an utterly opaque type that you need a sort of PhD to understand, he gives you several simpler types that make a lot more sense. So they're worth looking at. And there's tons I haven't told you. I mean, really a lot that I haven't told you about. But I don't understand most of it myself. So the place I'd like to finish is just to point out, look at what's happened here. We've got a library with, in which a lot of all the code, as I've shown you, has been really quite short. And what key features have we used? We've used the ability to abstract over type constructors. So a lot of abstraction over things of type star to star. We've used higher ranked types. That is, the lenses themselves are polymorphic functions. We've used that a lot, right? And we've used type classes. Those 3 things are really the kind of core pieces that lens uses. And that, on that, it builds an amazing amount of abstraction. I don't think we've had any clue when we were first designing Haskell that you could do this kind of thing. We probably would have run a mile. So I think it's really quite amazing how much power you can get, abstraction power, from these 3 simple facilities. So I think it's quite a remarkable achievement, the lens library. Let's have any more questions and comments before we wrap up. Yeah. Peter. I was going to say something about that, but I didn't have time to. So there's a little plan at the moment. This is about records in Haskell. So with Adam Gundry, we're finally doing the very simplest thing we can do to allow you to use the same field name in multiple records. So at one level, it's orthogonal to lenses, in that we're just going to give you a type class has, which says this record has a field f. And then that allows you to use the same field f in multiple records. And then we've got a way of allowing you to take, so now you've got a field f, which is a first-class value, and we're going to give you a sort of 2-lens function that takes the field f thing and turns it into a lens, essentially. So I didn't have time for that, but yes, so records are going to get a little bit better. Not all the way to wonderful extensible records, but just the smallest increment that gets rid of this ugly warp that you can only have the same the same field name, or you can only use a field name once, which is really annoying. So that'll be, that won't land in 7.8, but it will be in 7.10, and it will be in head soon. After we fork for 7.8, you'll see it in the 7.10 head branch. Yeah. All right.